Microphone check, 1, 2. All right. Hey everyone, it's me, Ray Long. This is another episode of Full Stack Distributed Systems. Today we're going to continue working on our universal wargame engine. More specifically, we're working on a subsystem, a topology and weight evolving artificial neural network. That's right, it's basically a very interesting and powerful artificial intelligence system that's going to be capable of doing genetic algorithm based machine learning. What does that mean? Basically, we're going to solve problems the way nature solves problems, using the mechanisms of evolution. It's a very, very interesting way to solve problems. Gives very interesting and powerful results. And so far, we've created our species class, and now we're working on our neural network. So, all right, we're going to jump into Visual Studio. Visual Studio protocols. Fantastic. We're going to get the music going. Alright. So where are we here? Well, we've got our class. It's going to be a neural network. It's going to be serializable. It's going to be important later on when we want to transmit our neural network objects across the network. Maybe that having an eye receptor is not the best. Well, we'll see. Basically, we'll be able to put in this container of receptors, anything that implements the eye receptor interface will fit in that container. You can think of a list as a container. And the angle brackets as the type that it contains, right? So, pushable receptors. What are these? These are going to be a list of things that we can push signals to. So. We're going to need a way to track our inputs. At least, specifically, we're going to want a way to count them. Let's make a new property called input count. It's hard to describe right now why we're going to need them. So, but basically, we're going to use them in our calculations, obviously. Sorry, that was a really wonderful explanation, I know. Okay. We actually can just do a private set. Thinking about it, like I said, I've made one of these before. And so we want our receptors, count them, and is there any kind of... Do we need to do anything? No, not ref. We're missing something here. Yeah, we can't actually do it this way because of the version that we're of .NET that we're using. So, and also that might just be bad code. That's what I'm trying to get rid of this for now. Let's make the get work, then we'll worry about the set. Okay, so we want var count equals 0, return count. Okay. Now we have We don't want the private. I don't know why I'm messing around with this. I'm getting distracted. Sorry, ladies and gentlemen. Let's focus on the input count here. So what we want to do is we want to make sure we count the receptors, right? So we'll do for each var r in receptors, if r dot type. This is ridiculous. We don't need to do this. You know what? Let's we might need to do this. Let's actually, no, not that. Let's take this I receptor interface. We don't need to make this internal. Well, we'll leave it internal, it's fine. We're going to call this receptor. And this is internal class receptor that implements I receptor. There we go. Now, where were we? Okay. It's a receptor. Standardize our code here. Our style should be consistent. Okay. That expresses it. There we go. So there, now we can get the input count. We want just the actual receptors. Let's add it to do here, though. Re-examine for pruning. Removal. Here, by way of refactoring. There we go, by way of refactoring. That might be unnecessarily complicated. Now we need to get the, oh, you know, of course, the inputs and the outputs are going to have to match up along certain rules. Whether that rule be a 1-to-1, a 2-to-1, whatever. Point is, we're going to have some rules that are going to be expressed for getting the inputs and outputs. And those constraints are going to have to be met in order for our neural network to perform. So this we actually just want to return the amount of effectors we get if it'll work. Okay, good. What's next? What do we think we're going to need next? Well, let's have a, we may as well have a synapses count, right? Yeah, synapses count. Why not? Well, I'll tell you why we should, as opposed to why not. Let's not be apathetic here in our development. Similar reasons we're going to want to count these. Oh, let's go and refactor this. Control Shift R Shift Control R Shift R. Synapses. There we go. Change the forest. Rename refactoring is complete. Of course, we're going to want the neuron count as well. neurons count, of course. Turn neurons.count. I don't want to have to type neurons.count a bunch of times. Although, arguably, neurons counts is not better. Neurons count. Oh yeah, well, it'll save us a hop. That's fine. At least in our typing. Alright, we're going to have to make some constructors. Since our neural network builder is going to provide the instance, we're going to keep the constructor internal. That way, outside consumers of the neural network package will have to use the neural network builder to provide them with an instance of the neural network class, right? So that way, the builder, like a choke point, you know, the builder is responsible for enforcing the rules for building a neural network that can work in this system. So there we go. All right, we're gonna need to get our receptors. All right, we'll clean up this code. What are we doing? Okay, yeah. What else do we need? We need our synapses. Synapses. We need our neurons. Yeah. What else do we think we need? Oh yeah, of course, our effectors. Effectors! Alright. It's kind of a gnarly looking, let's do this. Oh, that's a nice constructor. Go. Let you know what time it is here. Okay, so let's just assign away. Receptors equals receptor. Synapses will be assigned the synapses, of course. Oh, you get the idea. Our neurons will be assigned our neurons parameter. Effectors, same thing. And now we're also going to have our pushable receptors. We're going to assign that a value. What do we think we're going to need? Well, let's get system.link in here. Because I have some lambda action I want to. Oh, why did I guess I already. There we go. Okay. What do we think we're going to need for pushable receptors? How about receptors? Where what? Let's get our receptor. I bet you we could go back and refactor the other code. Probably want this to be type of receptor. Now from there, let's select actually cast it to this type. This is the actual explicit type that I want. And from here, we'll make a list. And then we'll break this down. We're not going to just glance over this. Not implicitly type. We actually can get rid of that entirely and just do toList. There you go. Because here's the thing. A receptor is an iReceptor. There's going to be various types of things that are going to descend from one another. We didn't really go over the class hierarchy as I have it in my mind, but it'll make sense as the code unfolds. So, since I really don't want to take out time to bore you with all of that wonderful stuff, we'll just keep going and writing the code. So, all right. So now that we can build this, we can have our pushable stuff, right? Because here's what I think. I envision that we're going to have iReceptor might need to have a name change later, right? Because essentially, I think Synapse, Neuron, and Effector, they're all going to inherit, or they're all going to implement the same core common base interface. And that's why I sometimes want just the receptor for the pushable receptors, because a receptor, we should probably, instead of having iReceptor, we should probably have iNode, since this is a network node. We probably should say that a receptor is probably a type of iNode, but let's add some notes for later. So that way I can preemptively answer questions I know would come up in a code review. Consider renaming iReceptor by network node. There we go. Okay. Now we need some methods. We're going to need some utility methods. One of the things that we want to hide and encapsulate away from our consumers is the ability to push data to the receptors. Okay? We don't want people other than us to do that. Okay. Only internal operations should be able to modify the internal state of the neural network, especially the receptors, right? Because the receptors, we're going to be pushing the solution to the receptors, and we don't want other objects outside of that receptor to be able to modify that data. So, which, by the way, if you're good at reflection, all that shit goes out the window, but that's some deep dark magic we're not going to cover too much today. Let's see. So that's what we're going to need. We're going to need a private void method. Now we could say this could be a boolean, it could be a true or a false. If we ever need to know if this was successful or not, we could always refactor it later. One of the things I like about the Go programming language, for example, is that I can have multiple return values from a method. It's something that you can't do in C#. So some would argue that's a flaw in Go. Others argue that's a strength. So push data to receptors. Let's just take a params of go back to our species. I think we're using floats or doubles. We're using doubles, right? Yeah. Right, we're using doubles. So we're gonna have various amounts of arrays of doubles, right? We should have some internal logging, but what do we want to do? So we want to say if the values dot length is greater than or equal to 0. No, that's not it. If it's not equal to the pushable receptors dot count. If we have more values to push than we have receptors, yeah, we want to throw out a new exception. Do we have runtime? We have a runtime exception in C#? No. Just do a regular exception for now. Execution engine exception. What is this? This is interesting. Let's go see the source code for this. F12 on this beast. Do you got any comments? Huh. Oh, this is in the interop services. I want to look this up real quick. Just take a moment here to do a quick Google search, see if there is some other intent, because this might actually be exactly what I'm kind of envisioning needing. Nah, it's been made obsolete. So we don't actually want that. We'll just we'll keep it simple. We'll throw a regular exception. But what this actually means, instead of grasping and reusing an exception, I forgot how to do a string formatting in C#. Let me just look it up real quick. I want to do string interpolation in .NET. I don't know if I can do it in this. Okay. Let's do this. Length is not equal to receptors. Now we could do the length, and then we can do pushable receptors. Clean this up a bit. Okay. Okay. So if we can proceed, then let's see how we're going to proceed. So we actually want to go. What's our condition here? It's going to be length. So we're going to spin through these with a for loop. What do we need to do? Well, we need to go to our pushable receptors, and this is why the length is so important. We need to set the charge, and that's how we do it. Oh, but look, this doesn't exist, right? So we can have the IDE add this member for us. So now iReceptor. Any iReceptor interface has to implement a property called change with a get and a set, public getter, public setter, and it returns a double. We can verify this by going to our iReceptor interface and seeing the brand new. Right. You can see undo, and if we redo, just Control Y, we see it. So there we go. Very good. So now we're pushing data to receptors. Here's what we need to do now. We need to solve this neural network beast. We need to solve it. We need to come up with a solution. That's right. How do we want to do this? Well, here's the thing. I'm going to produce an IEnumerable of doubles. When I solve this. Now what we're going to do here is we're going to go and spin through our neurons and have each neuron attempt to solve, actually not the neurons, we want the effectors to do the solving. We want to reset the neurons. Yeah, that's what we want to do. So we're going to do neurons for each, because we want to, neurons are going to have the previous state. They're going to have their calculated state that we would have pushed ahead to our receptors. We want to clear these out. Call the reset method. Doesn't exist. That's okay. We'll add it. So now if we go into our neuron class, we'll see. Good. Back to neural network. Okay. How are we going to solve this? Well, the solution lies with the effectors, right? So we need to spin through the effectors and basically call the solve method. So, see effectors dot for each. Make an object called E. Solve, right? Is that what we want? I think so. I think that's what we want. That sounds about right. So let's make this method. We'll stub this out in our effectors class. And then after we spin through these, no. We want to select these and then return them. And let's have this return our double method for us. That should make the neural network happy. There we go. Fantastic. That's how we solve it. We'll put our solving logic in there later. Thinking we're probably going to need to overload this solving method, at least if we're following along with the best we can. If we're following along with the handbook, we're probably going to need to overload solve. Push the data to the receptors. Go. We're just building it up piece by piece. You see? We already know what push data to receptors means. We know that solve has a meaning, right? So we go into solve, we say we're going to reset all of our neurons, and then each of these effectors we're going to create an array, let's say. An array of doubles from solving. Have each of these effectors solve the problem at hand using the fitness function. I don't know if it's the fitness function, I forget. Yeah, that comes into play. Anyway, it doesn't matter. So now we also need to be able to solve, we did all of them at once, we did an arbitrary collection of them, and now we need to be able to solve one, right? So, it's going to be just Now we're going to get into some interesting stuff here. How do we solve for one value? Well, we need to check the pushable receptors count. Got to make sure we have some. Make sure it's not equal to 1. And the effectors, we gotta have more than one of those as well. More than one, or maybe just not one. Let's think. Throw new. Let's see, string.format. Single value. But what? But pushable receptors count not equal to 1. And what else? My effectors dot count is not equal to 1. What do we need? We need value. We need pushable receptors dot count, and then we need effectors dot count. Let's make this a little better if we can. It's kind of hard to read. So if that's the case, we should break that string up into its own separate line, but I think it'll be okay for now. Okay. Oh, guess what? We're doing this again. We need to refactor this out. And do a single method. Alright, so we want to take the pushable receptors. There's only one of them. This charge will be the value. Right? There's the result. Have it solve. And then we'll return the results. We may have to do some loop detection later, you know, but we'll worry about that bridge if we need to cross it. Okay. What else do we need? Oh, wait. This is probably going to have to be public. Of course. Yeah. And this one should be public as well. We're going to need these later. Find all references. Do we reference this yet? Yeah, we did. Cool. Do we reference this? Find usages. Find usages. Find all references. Shift F12. We haven't used that one yet. It's okay. We need to gather some kind of metrics. should recite the metrics. Is that what we want to do? I want to recite the metrics. Yeah, let's call this what do we want to do here? Well, we're going to take each of the effectors for each RE and effectors. E dot. We need to pass a pass metric of 0. I know it's weird. Let's go to this. What should our input be on our effector? What do we think we're going to need? I know what we're going to need here. We're going to need an iComputing node. Okay. And when we build the effector, oh, this is oh, I did that all wrong. Wait a minute. Actually, let's do this. Internal effector. Yeah. So input equals the input. And that's it. That's all we want to do for the constructor. And now we want a public double method called solve. This is going to do is we're going to return the compute method on the input, and that's what we want to do. Too easy. And now pass metric be on the interface. There we go. See? Now I know what I need. Since I'm using interfaces, I can evolve the code as I need to, and I can worry about the implementation details later. I can code against the contract, you see. I can logically think about the contract that my data has to live with, all these different contracts. I can worry about the implementation details later as I go to flesh out each individual class of object, right? And that's the power of what we're calling next level engineering. You know? Be effectively, efficiently lazy in the best possible way. Defer doing hard work until you need to do it. Do the correct stuff do the easy stuff now and do it correctly and lay a proper foundation for all the hard stuff that's going to come later, right? That's our neural network. Now, see, I can read this code. I know what it does. I can say I'm going to spin through my effectors, and for each one of these, I'm going to call the input. Since this is all like local to the package, I can do this and get the field and just call the pass metric. So it's all internal to the package. That's it. That's all I have to do for my effector. Oh, and you know what? Wait a minute. My effector, I think I'm going to need to make this serializable. I think I'm going to want to not only like serialize this in a binary way, but I think I'm also going to want to transmit it over the wire with our distributed system, right? So since our internal state is going to be, you know, mostly binary numeric data anyway, should be pretty simple. What else do we need to do in our neural network? Is there anything else we think we need to do right now? Recited our metrics. Oh yeah. We actually might want to know. Wait, what is? Oh yeah. Do want to be able to detect, because we want to, if we're looping over a segment of our neural network, we probably don't want to do that infinite number of times, right? And we want to know if inside of our collection of neurons, if any of them exist, if any of these ring true, then we're going to return true, right? So neurons, we need a loop detected field or property. Let's do that. Bada bing, bada boom, easy. Let's go look at the definition. F12 on this BC. Get internal set, perfect. Worry about reset later. Go back to our neural network. I think that's it for the neural network. Go back to our neural network builder. Just think about our code here for a moment. What are we trying to accomplish? What do we want to do? And are we doing the right thing to bring our design into life, you know? Those are the questions we need to be asking ourselves continuously throughout the process. What problem are we trying to solve? And the answer should be consistent, and we need to use that to guide us in our development efforts. It's that simple. I was about to commit this code and push it up, but my internet seems to be intermittently getting all wacky here. Oh, now we're back online. So let's review this code that we have here so far a little bit. These are the read-only fields that we're going to have here. Collection of receptors. We're going to have synapses, neurons, and effectors. It's all very neural networky. Internally, we're going to have a collection of things that we can push to. We might have different types of receptors, but the ones we can actually push to are going to be a type specifically called receptor. So, okay, maybe get some counts back. Here is our internal constructor that our builder is going to use. Push our data to our receptors. want to start with the same. Okay, so here's the thing, actually, yeah. We want to... Okay, good. Wait a minute. Let's just double check this again. Okay, I got the alarms. Okay. It's gonna be weird, but you know, we're gonna put some logging in here. They're out this later, so I think I might have bugs in my logic, but it's okay. We want to go back into building a fully connected. Oof. We need to return this with receptors. Right. We need synapses now. We need neurons. And we need effectors. Okay. Let's generate these variables. Get a local. We want these to be local variables for now, I think. We want these to be local? Yeah, we're going to make these be local. Generate variable, we'll generate local effectors. Oh, we want neurons as well. We actually don't want these to be null. We can make these a new list. I don't like... You know, I don't want to have to... .network nodes. Let the IDE do some of the work. Some auto completion. Simplify these names. Code tighter, cleaner. Okay, now we have to make some logic. We don't want to return empty stuff, right? We're going to need to probably spin through our receptor count. We need to add some receptors. The first thing we need some place to put our results, right? So we're gonna spin through these. Less than the receptor count. We need to add new receptor. Fantastic. Okay. Bias equals new. We need a new network node called a BiasReceptor. This is basically exactly what it sounds like. It's going to receive data, and it's going to work on a bias. You know, it'll be swayed left or right, positive or negative, up or down, yes or no. The point is, there's going to be some kind of bias, and we're going to capture it. So let's go ahead and make this in our network nodes. We have a receptor. Copy and paste this. We'll rename it. I think we're probably going to want this to be serializable. I think all these quote-unquote network nodes are going to probably be serializable, right? So BiasReceptor. Yeah. Serializable. And then this will be not implemented yet, which is fine. We could just make this a get and set. It's gonna be crazy. Okay, so let's go back to our builder. We have our BiasReceptor. Okay, what are we gonna do next? It's a good question. Let's think. We're gonna build our fully connected neural network. What do we think we need to do next? Well, we're gonna build layers, right? Probably need to walk them all. And you know what, we're gonna have to refactor these out. We need a layer somewhere. Excuse me. Layer is gonna be less than the neurons on layer dot length. We'll go ahead and do that. A little bit of funkadelic shit in here. And now we're gonna probably have to we need to make neurons, but off the top of my head I can't think of I don't want to make a nested loop, but we'll do it for now. This sucks. Layer we're on, and then we're gonna layers to reduce space-time complexity of the neural network building algorithm. Go. We are going to need to reduce the space-time complexity of this by removing the nested for loops. Now we're going to need some synapses to connect to our current neuron. So here's what we need: some rules, right? So if we're on the first layer, synapses are connected to the receptors. Else, the synapses are connected to the previous layer. So basically, if you want to figure out why I'm doing it this way, the short answer is you should read the Handbook of Neural Evolution through Erlang The long answer is go learn Erlang to, and then come back to me after you read that book. Since I've already done that homework for you, why don't we go ahead and just write this in C#. So, receptors. We're going to select which one we want. We want receptor. Oh. Okay, so Synapse. Make a constructor in Synapse that accepts this type. Oh. Passing the receptor. What do we do to Synapse here? We don't want receptor. There we go, it's a little cleaner. If that's not the case, we have some other logic we need to do, right? So that's, now we need to connect to the previous layer. This time we're going to grab the neurons. Where? Neuron, layer ID. Want the previous layer, right?
Any ideas?
Then we'll take that, we'll select it. Probably want to make a new synapse with our neuron in there. And we'll make this to a list. We're not greedy. Make it a list. I don't know this be anything. Let's just go ahead and generate this property. There we go. Fantastic. Now that we've got our neurons and our synapses and all of our parts kind of plumbed a little bit here, start taking into account our bias. Okay, so now let's take the current neuron is added. What's going on here? I would have typed better variable names, that would have been a problem. Alright. Okay. Our neuron is added to its synapses, including the bias. So synapse is the current neuron. Dot add synapse with our bias. We'll say our current neuron. We're going to take a new neuron. Let's take our activation func. What else do we think we need? Oh, we need the synapses, of course. And we need the layer. Let's generate a new constructor for this. And we'll clean up our code later. Fantastic. Actually, let's take a look at that constructor now. Cool. That works for me. Turn them into properties later if we need to. Let's add our neuron. And now we have a range of synapses to add. And now we probably need to am I on the right? Okay, yeah. Okay, so if the layer, this is kind of confusing, I'm trying to keep it all in my head, equals neurons on layer. Last time I was off by 1. Last time I worked on something like this, so I'm always like, counting can get a little wacky. So let me add ourselves an effector, get a new effector, take the current neuron. Let's generate a constructor for that. Very good. Add our more bang bang. Let's randomize. Let's take our synapses, randomize their weights. And then I think we just want to return our neural network object. Alright, let's make this. Okay. Randomize these weights. We have a list of synapses, so what do we want to do? Well, we probably want to say we can just spin through them. It's going to need a weight property, and we'll say network till we need to get random weight. So that's pretty much it. So first thing we need this property called weight. I need a static class. Add it. Okay. What's the weight going to be? A double? Oh shit. Go to F12. Yeah, the weight should be a double. Very easy. We're going to use Unity engine random dot oh. You gotta. We have to use the engine. I need to cast. Will it automatically cast floats to doubles for me? It looks like it will. Yeah, this is what we want. We want a random number between 0.0 and 1.0. Okay, and that's going to be the weight. We're going to keep it real simple. A lot of numbers in between 0 and 1. So, alright. What else would we need in our builder? One of the things... Alright. Okay. So this video, we're a little over an hour. So we're going to do one more thing in this video. And that is we're going to create our fitness function. Or at least the core of our fitness function. Okay. We're going to effectively make an approximate hyperbolic tangent function. Okay. I know the math is going to be a little weird, but we want to approximate it. This isn't going to be a true hyperbolic tangent. We actually have some constraints on it that we want, just to make the shape. You know what? Actually, you know what we're going to do? Okay, let's think for a second. Public. We actually make this. approximate hyperbolic tangent. There we go. We're going to save this for next time. Or approximate hyperbolic tangent. It's not going to be a true, accurate, precise hyperbolic tangent. It's going to be an approximate one. Because we want, basically the way this works is the neural network is going to try to approximate values closer and closer to the hyperbolic tangent of the graph that it's trying to solve. Okay, that's just basically the secret sauce behind how all of this works. If you have a bit of a math background and you want to chew on that for a while, that's cool. If you have a software development background, you want to chew on that for a while, that's cool too. But otherwise, basically what this means is the way the neural network is going to solve problems is by trying to fit a shape on a graph. And if the shape fits, then the values it used to solve it are probably correct. And we do this enough times in a short enough amount of time, and this is basically how we solve problems using our neural network, and how the data flows through each neuron and synapse. We'll get into that more. And one of the things that I want to do in Unity actually is animate the flow of information through the neural network. But anyway, thank you so much for checking out this video. I hope you found it interesting. If you like, go ahead and like and subscribe. Check out Patreon or Facebook or Twitter. I'm active all over the place. I'm always hacking on stuff. So we're going to build this neural network to completion, and we're going to wire it up into our universal wargame engine properly once it's done. This is basically going to be a reusable AI subsystem, which will also be able to stand alone as its own neural network. So anyway, thank you so much for checking this video out. I had a lot of fun programming it for you, and I hope you had a lot of fun watching it. And I'll see you soon. Thank you so much. Bye for now.